Okay, in the last few minutes of the second meeting, I present some classical results on expected utility. I expect that many of you already know them from other courses, and it's easy. If it's new to you, then it's not table homework, but it's very important. They are very pretty results, very useful, widely used, important. You really should study them. So now I present them. First, let us assume expected utility. Then we have risk aversion if and only if utility function is concave. It feels a bit strange always that your risk attitude would be captured by how you feel about money. You feel that aren't they different things? But then if one's under expected utility, we can prove mathematically that it's true. So there's no discussion. The moment you have accepted expected utility, this is what it is. No debate possible. Risk neutrality, utility linear. Risk seeking if and only if utility convex. We can also do comparative results. We can have two decision makers, preference relation subscript 1 of the decision maker 1, preference relation subscript 2 of decision making 2, and then let us look at some condition, how to compare them. Here it is, and some notation that I use in this course. Greek letters usually denote outcomes, so things you get for sure. Roman letters usually denote the prospect that you choose from. In this chapter, they are lotteries, probability distribution over money. So now let us look at what this condition says. It says whenever, so for all, often I don't write the for all quantifier, whenever a sure outcome alpha is equally good as a risky prospect x for decision making 1, then for decision maker 2, we will want to go for the sure option. So decision maker 2 more often goes for certainty than decision maker 1. That we define to mean risk, that decision maker 2 is more risk averse than decision maker 1. And I think it makes intuitive sense. A theorem, if we have expected utility for both decision makers, then decision maker 2 is more risk averse than decision maker 1, if and only if the utility function of decision maker 2 is a concave, so phi is concave, is a concave transformation of the utility function of decision maker 1. This result quite naturally fits with this result. Risk aversion if and only if utility is concave, more risk averse if and only if more concavity is brought in the utility function. So that makes quite some sense. Another equivalent way to formulate I give below. So decision maker 2 is more risk averse than decision maker 1 if and only if this number here, we'll look more at it soon, is exceeding that number always. This means for every outcome alpha, you can calculate the second derivative of the utility function, decision maker 2, first derivative, and minus that divided by that is that number at alpha. For decision maker 1, you can calculate that same number, index at alpha. Then more risk averse holds if and only if this index always exceeds that index. So this quite suggests that this maybe weird looking fraction at first sight, that is a good index of risk aversion, and so it is. These numbers are often used as indexes of risk aversion to quantify them. They are, sometimes they say in an absolute sense for all kind of reasons. They call this the Pratt-Arrow index because Pratt-Arrow independently discovered it. In fact, De Finetti, you heard the name before, discovered it before them, but people call it usually after Pratt-Arrow. There's also another index that is commonly used in the literature for if you have only positive money amounts, then if you multiply this index by the money amount alpha, you get relative index of risk aversion. For many purposes, that is a good index. So several kinds of indexes are useful for several kinds of purposes. Here is yet another formulation equivalent to what we saw already. Decision maker 2 is more risk averse than decision maker 1, if and only if decision maker 2 has bigger risk premiums than decision maker 1. The risk premium is defined for every lottery, the expected value minus the certainty equivalent, that is defined to be the risk premium. If a person is risk averse, then the certainty equivalent is always smaller than the expected value, so then the person has positive or non-negative risk premiums. Risk aversion, if and only if risk premium non-negative. And here, more risk aversion, if and always bigger risk premiums. Risk premiums are of special interest to insurance companies because they indicate the profit margin. Because a risk for the insurance company, the value is equal to expected value, but for the individual, the client, the value is equal to the certainty equivalent. So if the insurance company takes that risk over from the client, then the difference between the values is a profit margin. Therefore, insurance companies are much interested in risk premiums of people. We can also do comparisons within a person, see what happens if a person becomes richer. And usually we find that people, as they get richer, they become less risk averse, so decreasing absolute risk aversion. I give now the definition of it, and it goes like this. Imagine some decision maker, a sure outcome or a risky lottery, person is indifferent. Then if we add a positive epsilon money amount to both, we could, for instance, add an epsilon amount to the bank account of the person, and the person gets more inclined to go for the risk than when he was poorer. So this means as the person gets richer, he becomes less risk averse. This is decreasing absolute risk aversion. It's a common empirical finding. Anyway, these were a few very shortly presented. The book gives more results. You should study them and know them well. But this is where I'm going to end the second meeting. And the third meeting will be on uncertainty, but that will come in the next meeting.